In this video, I want to look at integrals involving powers of sine or powers of cosine. They're actually very similar in how we handle them, um, so we'll take a look at them. The simplest one, of course, would just be sine to the first power, which is cosine x. No, it isn't. The derivative of sine x is cosine x. The antiderivative of cosine x is minus the cosine x plus c. And likewise, the antiderivative of cosine x is the positive sine x plus c. Okay. Um, Sine squared and cosine squared are a little trickier to do. Um, actually, yeah, let me come back to sine squared and cosine squared. I'm going to take a look at if I had something like sine cubed of x. Now, in a previous video, I did a telescoping integral for sine to an n. I'm going to do this one a little differently, just because it's pretty easy to do a little differently. Um, I do it this way. In fact, sine to any odd power, I might be inclined to do this way. I'm going to leave one sine alone, and then think of the rest of it as sine squared x. Right? But the sine squared x is 1 minus cosine squared x. So this integral right here is equal to this one, which is equal to the integral, I'll write this first, 1 minus cosine squared x, and then times the sine of x. Notice now I have a really nice u substitution because I've got cosines and sines together. If I let u equal the cosine of x, then du is minus sine x dx. I'm missing a minus sign, so let me throw times minus 1 in there, and let's throw a times minus 1 on the outside. The net is the times 1, so we didn't change the value. So I've got a minus the integral of negative 1 minus, oh, sorry, this minus sign goes away because the minus sine x dx is the du. So I've got 1 minus u squared du, which integrates to minus u plus u squared, u cubed over 3 plus a constant, but then u is cosine x. So I've got minus cosine x plus cosine cubed x over 3 cosine cubed x over 3 plus a constant. Okay. If you've got an odd power of sine, you take one of them and then you got an even number of them left. Each sine squared turns into a 1 minus cosine squared, right? So if I had a similar integral of, say, sine to the fifth x dx, then I could think of that as sine x times sine to the fourth x dx. And the fourth is sine squared squared. So I've got a 1 minus cosine squared x. That would be sine squared x, but then I have that squared. I've got it twice because it's the sine to the fourth power there. There's still a sine x left over. Right? Same u substitution as I did over there, I do over here. I need an extra negative sign in there and a minus sign out there. Anyway, I end up with minus the integral of 1 minus u squared squared du. Right? Now, I got to do some algebra, multiply that out. So this is minus the integral of 1 minus 2u squared plus u to the fourth du. But I can integrate that reasonably easily. So I'm going to distribute the minus 1 as I go here. So minus u plus 2u cubed over 3 plus, no, minus u to the fifth over 5 plus a constant. And so then you plug the u back in, and you've got cosine x plus 2 cosine cubed x over 3 minus cosine to the fifth x over 5 plus c. Okay. And in a similar way, any odd power of sine can be done that way. Likewise with cosine. If you had cosine cubed, it would look very much like the sine cubed integral. The integral of cosine cubed x dx, I would write it as cosine x times cosine squared x. And then the cosine squared x is 1 minus sine squared x. So I've got that 1 minus sine squared x times cosine x dx. This time I want u to equal sine x, and du is cosine x dx. Sine and cosine are really nice. They go together trigonometrically, like there's this trig identity that turns cosine squared into 1 minus sine squared, vice versa. And they go together calculitically, whatever, but related by calculus. That the derivative of sine is cosine, the derivative of cosine is minus sine, that that all that works together to make these integrals reasonably easy to do. Right? Anyway, I've got the integral of 1 minus u squared du. This one's even nicer because you don't have the minus sign floating around there. Anyway, this is u minus u squared over 3 plus a constant. U was sine x, so sine x minus sine, that's a cubed x over 3 plus constant. Okay, so odd powers of sine and cosine are nice. You pull one of them out, and you got an even number left. Those even number turns into 1 minus the other one squared, and then you do a nice u substitution. Okay, so that's, did I say even? That's odd powers of sine and cosine. What just happened? Odd powers of sine and cosine. Now, what about even powers of sine and cosine? The first one that we're going to deal with is sine squared x. Okay, I'm going to use an identity that is a power it's called a power reducing identity. Sometimes it's called a half angle formula, but I write that a little differently. The sine squared of x is equal to 1 minus the cosine of 2x divided by 2. Okay. This comes out of the half angle formula, and I have videos posted of a bunch of trig identities and where they all come from. But anyway, this is what's called the power reducing formula for sine. And so this integral right here can be written as the integral of 1/2 times 1 minus the cosine of 2x dx. The 1/2 can be written out in front, and you just got 1 minus the cosine of 2x dx. Okay. The 1 is easy enough to integrate, right? This is 1/2 times x, and then the cosine of 2x is actually u substitution here with u equals 2x, so du is 2 dx. So there's a factor of 2 that I'm missing, so I'm going to end up with an extra 1/2 here, the sine of 2x plus a constant. 1/2 x minus 1/4 sine of 2x plus a constant. Likewise, with cosine squared, so if I want to do the integral of cosine squared x dx, I'm going to use a similar power reducing formula to this one up here. It looks like cosine squared x equals 1 plus the cosine of 2x, all divided by 2. So this integral right here becomes the integral of 1/2 times 1 plus the cosine of 2x. And we'll do the same thing. The half can come out in front. And then you've got the integral of 1 plus cosine of 2x. So that's x minus 1/2 sine 2x plus a constant. Again, I did a u substitution here with u equals 2x. So du was dx. Sorry, no it wasn't. It was 2 dx. So there's a factor of 2 that I'm missing. That's why there's the 1/2 here. The antiderivative of cosine of u is going to be minus the sine of u. No, it's not. Hang on a minute. The antiderivative of cosine of u is plus the sine of u, so there should be a plus sign right here. And this one, yes, I was momentarily confused. I was thinking on one of these I was integrating sine, and one of them I was integrating cosine, but I'm not. I'm integrating cosine both times, but this one has a minus in front of it, where this one has a plus in front of it. So anyway, that should be a plus right there. And there you go. The integral of cosine squared x is done with a power reducing formula. Likewise, the integral of sine squared x is done with a power reducing formula. Okay. For bigger even powers of sine and cosine, I see a couple of different options. I'm going to scroll down below this page break here. Um, if I had the integral of sine to the fourth, the way the book suggests we do it is to um, think of this as sine squared times sine squared. So this is going to be 1 minus the cosine of 2x over 2 squared. Integrate that. Well, you got to multiply that out first. So it's going to be 1/4 times, and when you do a, you square that out, so you do a FOIL, it's going to be 1 minus 2 cosine 2x plus cosine squared 2x. And you see what happens is that you get another cosine squared, which you now have to do a power reducing formula on that. So you've got this is equal to that, is equal to this. So I've got the integral of 1/4, 1 minus the cosine of 2x plus 1/2 times 1 plus the cosine of 4x. So that power reducing formula with the 2x in there becomes a 4x. Anyway, and now you can integrate that. Okay. Likewise with cosine squared. Personally, I'm thinking, didn't we do a you know, didn't we do a telescoping integral in another video? It's like, yes, we did. We had an integral that said the integral of sine to the n x dx is equal to, what's it equal to? What did we get? We got -1 over n times the sine to the n minus 1 of x times the cosine of x plus n minus 1 over n times the integral of sine to the n minus 2 of x dx. Right? So if I'm trying to do a sine to the fourth power like this one, then n is 4, and I plug in 4 for n, and n minus 1 would be 3, 3 over 4, sine squared. And it's like, okay, sine squared. I can do sine squared because I did it up here. Right? So rather than, here's sine squared, integrating to this thing. So rather than attempting to do this multiplying out, and it's not too bad here with just sine to the fourth, because that's just squared. But if you had sine to the 14th, then you'd have this thing raised to the 7th power, and then that gets really big. That gets really big. And probably it would be better just to do this telescoping integral. Actually, this telescoping integral works whether n is even or odd. You can just use it, and then this will eventually get down to either sine squared of x, or it'll get down to sine x, depending on whether you started with an even or an odd here. Okay. Likewise, with cosine, we didn't derive this one, but in a very similar fashion to what we did for sine to the n, we could have done a cosine to the nx, and I'll just write down the formula here. It's done exactly the same way the other one is. 1 over n cosine to the n minus 1x times the sine x plus n minus 1 over n times the integral of cosine to the n minus 2x dx. Right? So any power of sine x or cosine x can be done with these telescoping integrals. With some of the smaller powers, I think it's easier just to do it for sine squared, for sine, even sine cubed. Not worry about the telescope. Anyway, there's sine and cosine. In the next video, we'll look at combinations of sines and cosines multiplied together.